Mungu ibariki Tanzania, dumisha uhuru na umoja wake kwa waume na watoto. Mungu ibariki Tanzania na watu wake. Ibariki Tanzania, ibariki Tanzania, tubariki watoto wa Tanzania.
How are you, everybody who is watching this fantastic video? I would like to take this opportunity to welcome all my local, national, international, and even none of my students into this fantastic program. Maybe you have been looking at an online advanced secondary school that can teach you the beauty of advanced physics, advanced chemistry, advanced mathematics, and basic applied mathematics. That can teach you online, anywhere, at any time. Or maybe you are an advanced secondary student who is trying to struggle on finding different ways to master your advanced subjects in your combination. Maybe you are Tanzanian, maybe you are non-Tanzanians. It doesn't matter. What I want to tell you that the answer of all those few questions that I've asked you or have challenged you at the beginnings of this session might be obtained in few minutes to come, or might be obtained simply in this program that I'm going to introduce to you. My name is Olenjolai Moko Tayelo Single. Simply just can call me Olenjolai. It's enough. I am a Tanzanian, so I would like to welcome all the Tanzanian advanced secondary students, whether pre-advanced secondary students or advanced secondary students or post-advanced secondary students. You are warmly welcome to enjoy the beauty of advanced science and advanced mathematics. I thank God by His own grace who has given me a gift of teaching. So I'm going to be your teacher in this program who will be teaching you about advanced physics. Then I would like to welcome you before I tell you about the vision. Secondly, I would like to take this opportunity to welcome you into one of our advanced secondary schools that called Tanzania Online Advanced Secondary School in square bracket OLENJOLAIM. However, that there on the blackboard, I have forgotten to include M. So mean the name of the school is that Tanzania Online Advanced Secondary School. And then I would like to welcome you into our official YouTube channel that's called Tanzania Online A-Level Secondary School in square bracket OLENJOLAIM. Even the name itself indicating will be focusing and will be preparing contents that will help all advanced secondary students. So the internet, and even can have them offline if you have more space. I'd like to spend 1 minute to tell you about the vision that we have in TOASO, because TOASO is the abbreviation of Tanzania Online Advanced Secondary School. This is the vision that you let right in your mindset. We have an assignment to teach and train advanced secondary students on how they can extract knowledge, understanding, and wisdom from the classroom instructions in advanced science and advanced mathematics, and combine it with knowledge, understanding, and wisdom that will teach them to extract it from the Word of God in order to solve real-life problems. The main objective of TOASO is to teach our students to think outside the box, and the main goal of these programs, after teaching our students to think outside the box, we teach them on how to solve real-life problems. Again, this is a warning I would like to give you at the beginnings of this session. Believe me, I don't know everything about advanced science or advanced physics or chemistry or advanced mathematics. I just know small portions of it. But I have an assignment to teach other students about what I know. I'm always learning, and my journey of learning will never end. I'd like to welcome you again into our departments of advanced physics, where we are teaching advanced physics Form 5, advanced physics Form 6, And the subject of the day is called Advanced Physics. And the main topic that we focus on today is called the current electricity. The second topic is for Advanced Physics Form 60. And these contents are dedicated to pre-Form 5, Form 5, Form 60, QT, reciters, Grade 12, teachers, and chemists. We are still in Chapter 1 that are called the Electric Conductions in Metals. Welcome into Session 10 that titled as Resistance Matching and Potential Divider. Possibly this is your first time to hear about that term, but don't worry because I will navigate with you. Again, I know some of the students have registered and actually have been my online students, and some of the students, it's your first time. Whatever your category you are, you're warmly welcome. If it's your first time, or if you have been watching our programs and you have never registered yourself, I would like to spend a few minutes here to navigate with you on few steps to register yourself in our online school. So join me within a few minutes to navigate. So if it's your first time, or you've been watching our programs and you've never registered yourself permanently, or you don't know how you can access our systematic contents in topics and subjects, then just join me in a few minutes to navigate with you. The first step, if you don't have an email, we ask you to create a new email. If you have the email and you remember your username and password, then skip this part. You can create either a Gmail or Yahoo mail. Okay, that's the first step. If you have an email, skip the first step and remember the password and the username. The second step, we ask you to sign in. Sign in YouTube. Remember that we assume that you have a YouTube application, whether YouTube mobile applications or computer applications. So sign in YouTube by using the email that you have created. The second step, we ask you to search what? Tanzania Online Advanced A-Level Circuit School in square bracket OLENJOLAIM in YouTube. Don't search it in WhatsApp. Don't search to us in Instagram. You will find at this moment we are sharing our contents in YouTube. Then the fourth step, then what will be the results of your search? You will see so many results when you write Tanzania Online A-Level Circuit School in square bracket OLENJOLAIM. You will see so many videos, but we will ask you to focus on the small round button which contains the Tanzania national flag. Beside it, it has been written Tanzania Online A-Level Circuit School in square bracket OLENJOLAIM. Below it, you will see the number of videos, and this is what we call it our online poster, our welcoming poster to us. Then we should not end there because you have just seen our online poster. We ask you to click the round button which contains the national flag, the national flag of Tanzania. Click the round button. So once you click the round buttons, you will see a banner, and this banner, okay, it has a particular photo which is very interesting that you'll find in Tanzania. Yeah. Just you'll see a particular photo of my people or a national flag. So it depends. So at this moment you can see the Tanzania national flag, or you can see just my people. These are my people. So you can see my people. My people, we met with them somewhere. And then below it you'll see again the round buttons, and then you see the names to ASO, to Tanzania Online A-Level Circuit School in square bracket OLENJOLAIM. But at the top of right hand side, you'll see a button written subscribe. So we ask you to click this button. That will be the fifth step. Click the button written subscribe, and then the text will change from subscribe into subscribe, and the icon of the bell will appear. Click this icon once, and then she asks you to choose the options of all. From there, once you accomplish this step, it means you have subscribed yourself, you receive all the notification whenever we add a new video to you. Okay, so you receive it at any time once you are online, once you have linked yourself online. Then, so from there, you have registered yourself It's one lifetime registrations. It's free. Nobody who's going to charge you anything. So you can register and then you can access and receive the new information or receive the official information from the YouTube community. The first step, we ask you to click, just to go here at the top, you'll see some words called home, video, videos, and then you'll see playlist, you'll see community, you'll see channel, you'll see about. So we ask you to click the button written playlist, and then we ask you to search a playlist written current electricity. So this is the navigation that we would like to navigate with you to access the collections of sessions of current from session 0 to the last sessions, and you'll find them, they have been arranged systematically from the first session to the last session. So we believe that you enjoy our content. So I think that you might be having questions. How can you share with other students? Okay, so click the icon share. So on your right hand side at the bottom, click the icon share to share the video link. This video means to share the video link to other students. And through or via social media. When you say social media, we have so many examples. You can share the video link. You can share the video link through WhatsApp, through Telegram, through Instagram, through Twitter, through Sasai, through TikTok, through your email. So you can share with other students around the world. You can share with other students in any advanced secondary school. You can share with other students who are in vacation. So there's no any limitation for you to just to keep on moving. So from there, you know how to register and you can share this information with your colleagues. You know how to access our contents, and you know now how you can share the video link to other students who are in the same class with you or who are away from you. Because the good things of TOASO, right now you can learn advanced education at any time and anywhere. Does it make sense? Thank you very much for registering yourself. So let us go into the next part in the quick review of the previous session. Let us dive into the quick review of the previous session, which we didn't upload it yet. And this is called the session 9 because when started session 9 precedes session 10. So in session 9, basically we taught you a concept or some concept that we have been teaching you since you are O-level education. And this is all about the arrangement of resistance. Arrangement of resistance. Okay, arrangement of resistance. So what we have taught you that resistors can be arranged in series. Resistors can be arranged in series, and equivalent resistance, which is I, let's say from I is equal to 1 to N, this is equal to R1 or R1 plus R2 plus R3 plus R4 dash 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 dash. So that the equivalent resistance for series arranged for series network. So just like this way, so this is series connection, R1, R2, R3, etc. Then we taught you about resistance also can be arranged in parallel. So in parallel, which is called parallel network. So when resistors are arranged in parallel, we have different current, same potential difference. Okay, same potential difference and different resistance like this way. This is R1, this is R2, this is R3. So we told you that the equivalent resistance, which it is 1 over Ri, from I is equal to 1 to N, this is equal to 1 over R1 plus 1 over R2 plus dash 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 dash. Again, that was not the case. We just reminded you about the previous concept. Then we told you about the complex network of what? Of series and the parallel parallel arrangement of 40 of resistors. So if you do remember that, for example, we have taught you to solve a problem where you can find the network is like this. So, and then you have to find the equivalence. This is terminal A and this is terminal B, for instance. So, okay, this is a little bit simple, but you can find that again, we have another network here of 40 of resistor. Okay? So you can have something like that. So we have been dealing with complex networks. So that's all. In case you missed it, just within a short time, you can access it in the playlist called The Current Electricity and in our official YouTube channel. That's called your Tanzania Online A-Level Circuit School. That's all about a quick review. Let us dive into today's session. Session 10, we are going to teach you about two concepts which are very important in physics and engineering. The first one is called resistance matching. Very interesting concept. And the second one, we call it potential divider. Remember that myself, by grace of God, have been going through advanced, just the higher physics in terms of or applications of physics in engineering. So I've done my degree in electronics and telecommunication engineering, and I want to tell you that the secret there is all about potential divider. So I know how important it is and how is it used to solve real life problems. So let us go into today's break. And in today's break, before I teach you about resistance matching, let me just give you the overview of the key principles of resistance matching. And let us start with the concept that we call it cell, arrangement of cell. Arrangement of or electric cells. So let me quickly remind you about electric cells. Electric cells. Okay? So electric cells, my physical students, you are sleeping. That is very bad behavior. So let us start with a fundamental question. What is electric cell? What is an electric cell? So an electric cell is a device, simple device, or we call it the source of electric current. That's a simple definition of electric cell. So it's a source or a device that produce or give us electric current. That's the first. So types of, so when you say that, so electric current device that gives is a device or source of electric current in the electric circuit. So electric cell, we say that this is the device or source of electric current in the electric circuit. The symbol of electric cell, just to remind you of electric cell, because you have also cell in biology, is this. Okay? So when you have a collection, so we say that we have battery is more than one cell. Okay, it's more than one cell. So when you combine two or three cells, and I believe that you've copied this instruction, then you form a technology that we call in physics a battery. So the simple connections of the battery is just like this. The simple connections of the battery. So we have two terminologies that we'll need to cover them, especially we'll be using them when I will be teaching about resistance matching and for the rest of the electric conductions in metals. And this is the terminology. The first terminology is called the electromotive force. We taught you about electromotive force in O-level physics. Electromotive force. And this electromotive force is called the EMF, in short. Electromotive force. Electromotive force is abbreviations of EMF. So what is electromotive force? That's the second question. What is, let us remind you, what is electromotive force? Okay. What's electromotive force? So electromotive force, we say that this is the internal, is a driving force of electrical current in the circuit. So electromotive force is a driving force of electrical current in the circuit. So it's a driving force of electrical current in the circuit. So electromotive force is a driving force of electrical current in the circuit. Okay, in the circuit. And there's a unit of electromotive force is volt. You know about it. Or you can define that as a total potential difference measured between the two terminals of the cell when the cell is not driving the current to the circuit. Or, this is a very important definition, EMF is total potential difference the total potential difference measured when the cell measured between two terminals of the cell when the cell is not driving electrical current in the circuit. Very interesting. So electromotive force is not potential difference, because potential difference is actual driving force, or is the total potential difference between, or is the potential difference across a conductor when the electrical cell is driving electrical current. So this one is measured when it's not driving the electrical current. So for example, if you have a cell like this, then ladies and gentlemen, this is what you call the EMF, or in other words, you call the electromotive force. Okay? So it means that the potential means if, for example, you take a multimeter and measure the voltage. So this is what you call the EMF. So this is all about EMF. When we say a voltmeter, because this is a real lifetime class, we are not talking about something huge. it depends. The voltmeter, it can have different shapes. Then I have a cell. So ladies and gentlemen, this is the cell, an example of the cell. So these cells, there has two terminals, positive terminal and negative terminal. This one is positive and this one is negative. So the bigger one, the terminal on the left hand side is negative and the terminal on the right hand side is positive. So this is the cell, right? If they are more than, there are two or more than two, it's called the battery, right? So this is the cell. So I have some physical students. So when you say voltmeter, we can get a voltmeter from multimeter. You have to listen. This is a multimeter. But within it, there is a direct current voltmeter and the alternating current voltmeter. AC voltmeter and the DC voltmeter. Similarly, this is another device that we call the multimeter. Why it's called the multimeter? Because it contains so many measuring instruments, so many electrical measuring instruments. It contains an ammeter, it contains a voltmeter, it contains an ohmmeter, it contains frequency meter, it contains a capacitance meter, so it contains diode testing, so it contains so many devices, measuring electrical devices. Are we together? So when you say that you want to measure, so can I have my cell? These we call them probes. I'm not teaching you about voltmeter. Maybe in the next sessions I can teach you because they're one of the instruments. So this is positive probe and this is negative probe. So for example, that if I want to measure the voltage across this one, one of the students can come and hold this, if you like. So this is DC voltmeter. So this is DC voltmeter and this is the display. Okay? So this is positive, so I have to put it here. And then this is negative, I have to put it here. So right now I'm measuring electromotive force, right? There is no any load consuming current from this cell, right? So what the reading? Can you read it for other students? 3.070. So it means that in our demonstration, in our demo, the electromotive force of the battery is equal to 3.070 volt. So this is the electromotive force. There is no any resistor or any load that consuming power. Do you understand? Physics is beautiful. Okay, so you can take this one to demonstrate others who are slumbering there. So that is about electromotive force, and it is measured in volt. You know about it. And then the next parameter, or the next parameter is called internal resistance. It's called internal resistance. So we talked about external resistance. So today we'd like to teach you about internal resistance because we need these technologies. If you have internal resistance, it means that we have also external resistance. So internal resistance. So we have the fundamental question 3. What is internal? What is internal resistance? What is internal resistance? What is internal resistance? So we define in physics that internal resistance is oppositional force offered by a cell itself against a passage of electric current. Internal resistance of a cell is oppositional force against offered by a resistor, offered by a cell against a passage. This is the passage of electric current within it. Within it. That's the meaning of internal resistance. And also internal resistance, its symbol is R, and its unit. I know for the most advanced students, they don't care about this stuff. They say, sir, they're just revising what we know. I know that you know, but just wait a moment. You'll see its importance. So, and what its SI unit is ohm. So, in previous session, we have talked about potential difference. We define it, we drew it, and we have talked to you also about external resistance. We've talked about external resistance. Okay? So, right now, let me leave the first homework in session 10. This is homework 10. And this is example, we ended the example what in previous session? Students, they don't remember, fortunately. So we ended in example 21. So this is example 20. We did example 22, so this is 23. Mention at least three differences between, so list the three differences between electromotive force and the potential difference. Mention also three differences between resistance and the internal resistance. That's your homework. Make sure that you do it before you make the next session. So, what are we looking for? Where are we going? I'm building the foundations of resistance matching in your mindset. Okay? So from there, so let me teach you the next part, which you call the power distribution. Power distribution in power distribution on electrical circuit. So the first is the consider the circuit below in figure 10.1. So this is our circuit. And then we have a symbol for them. So this is electromotive force. This is internal resistance. So this is a SAO. And then we connect it across the load resistance. And here we have the switch cable. So here we have external resistance R. So when you close the switch, then the current starts to flow from the positive terminal of the sub to the negative terminal. So positive to the negative terminal. So this is figure 10.1. called what? Electrical circuit. Electrical circuit. So the second step, we say that from Ohm's law, we say that electromotive force or driving force is equal to electrical current. But just Ohm's law, we say that voltage is very proportional to electrical current when other physical factors, when other factors are kept constant. So if you make the proportionality constant, you have resistance times charge. But for that circuit, we don't have electromotive force. The driving force is electrical potential, because this is potential difference across this circuit, for example. So electromotive force is equal to the electrical current. This electric current is being opposed by two resistors, internal resistor and external resistor. So R plus this. Okay? So from this expression, first of all, we covered it in previous session. We have electromotive force over resistance plus over external resistance plus or internal resistance, and this is equal to electrical current. So this is a very important expression on maximum power theorem that we are going to teach. Okay, so but our subtitle there is about power distributions on electrical circuit. That is just to reduce electrical current, it's equal to that expression. So the second step, if you want to know the power distribution, we have to recall the formula of 14 of power. So the formula of power can be expressed of electrical power, not just the any power, of electrical power. So the formula, we say that power, which you use this P, is equal to current times potential difference. So we say that power of the cell right now is equal to electrical current times electromotive force. But also this one, we say that if we use Ohm's law, this is equal to current square times resistance. But also we can express this formula as what? Voltage square over resistance. Over resistance like that. So when we discuss about power dissipated in the resistance, so power dissipated. So when we discuss about power dissipated, then we see that this is equal to what? So we say that is equal to current times what? Resistance. So when you want to find the power dissipated in the cell, this is equal to current square times total resistance, or the total resistance there. So power distributed, or actually the power, okay? Power, yes, okay. So power, yes, okay, it is power, it's still power. So power is equal to current, and then so what the total resistance? We have the summation of internal resistance and external resistance because they are in series. Right? If resistors are in series, then you sum them. So now, the power for that circuit, it will be current square times resistance times what? Times, or plus what? Times external resistance plus what? Internal resistance. But again, we can express furthermore, and we can open the bracket. So power is equal to current times external resistance plus current square times internal resistance. So the power dissipated in figure 10.21 for the power distribution now. So we say that we have current square times external resistance, then we have current square times internal resistance. So this is an important formula for the next few minutes. So remember that power consumed by load, which is R, is equal to square of the current times resistance. Then from that formula, I say that power lost, because this is the load, it means this is an electric appliance. When you say an electric appliance, because I know that I'm teaching advanced secondary students, I would like just to give you again a simple example of external resistor, because you've been learning resistor since you are O-level, and you thought that resistor is something else which you have never seen, and I want to disprove that it's not true. This is an electric iron. Stop writing. This is an electric iron. So in physics we call it load. Power consumed by the load. For example, if I connect this iron in the electric power, for example, that I have a cable here. So this, you see the red light now is on. So it means that the iron is consuming electric power. Right? So this is the simple alternative, just a AC resistor or load, because you cannot power this by using a dry cell. Are we together? So this is load, and this is what we call it resistor, or we represent it in physics by a symbol R. So I can just eliminate this one and then put an iron. Are we together? This is the simple meaning of 40 of resistor. I have some bunch of resistors which you use them in electronics, but I know for the many students they can think that resistor is something wonderful, something new. No. And that's our responsibility to expose you into the reality of physics. So when you talk about resistor, it's this one. So now, the power dissipated inside the cell, this we call it the power lost. Why? Because this power that overcoming means that this power which will be spent in internal resistance of the dry cell is lost because it does not have any use for us. So for that reason we say that power lost in internal resistance. So the power lost in internal resistance, which is R, this is given as square of the electric current, because we have electric current that flow in this direction, I, times internal resistance. So what do we do as physicists? Right? According to the experiment, in physics it has been shown that if we are not careful on choosing the value of resistor, we might experience the large amount of power lost in the cell due to the internal resistance rather than the power consumed by the load. Listen careful, I'm talking the truth about physics. Let me repeat. According to experiments that have been done by different physicists, including you can do even that experiment. If we are not careful on specifying the value of resistance, especially the external resistance, or the value of a load, resistance of the load, then we might find that too much of the power will be lost in the dry cell. Listen carefully. What are the functions of a cell? Where is my cell? What is the function of the cell? The function of the cell is to store electric power. At the function of the cell. If this cell is consuming some power while you didn't connect it in a particular circuit, that is a loss. Right? What do you think if you buy this with a price of 1,000, and then after one day you didn't use it, you put it on the table and you find it does not have any power. So where does power go? Where did the power go? It means that the power has been lost due to the internal resistance. So that's why that we say that in order to minimize the power lost by the internal resistance, so we say that in physics and the electrical engineering, in physics and electrical engineering, in order to minimize the power lost, okay, due to internal resistance in the cell. Then what do physicists and engineers, electrical engineers do? Then the load resistance should be large. Then the load resistance like an iron, load resistance like a bulb, load resistance like a fan, load resistance like your mobile phones, it's a load resistance. So don't think that resistance is something else new that you've never seen. That is not true. So then the load resistance should be large. Should be large enough. Why should it be large enough? In order to consume a large amount of power. Large amount of power. So that is the fact. So in most cases, or in most circuits, you'll find R is larger than this. And from there, physicists and electrical engineers, they deduce this something we call it maximum power theorem. Right? The aim of maximum power theorem is to maximize the power consumed by the load resistance rather than the power consumed by the internal resistance of the cell. So ladies and gentlemen, allow Olenjolai to teach you about maximum. Say with me, 1, 2, 3, maximum. Say maximum. My local students are quiet. They cannot speak. Maximum power theorem. Maximum power theorem. Say maximum power theorem. So this one will give us a first question for this session. State the maximum power theorem. State the maximum power theorem. The maximum power theorem states that so the maximum power theorem states that for the maximum power consumption of a load resistor, then for load resistance, for the maximum power consumptions of load resistance, the maximum power of load resistance needs for maximum power consumption of rod resistance require the minimization of power lost due to internal resistance. So that's the theorem. That's how maximum power theorem states. But this theorem is used to maximize power usage in electrical plants, okay? So this theorem, it used to maximize power usage in most electric appliances. When you say electric appliances, example, iron, example, heater, example, bulb, another example, fan, okay, another example, can you give me another example? Radio, it's electric appliance, another example, television, another example, what? Phone, handset, that's equal to telephone, etc. So, for example, you connect it, or let's say, for example, who has an electric phone, or who has a telephone which does not have a cell? Can you take your phone? Take your telephone. Take your telephone, and then you have to know, you can open it if it just equal to Kiswahili, you can open it and then you see its battery. But most of the smartphones, you find that the battery is sealed within the phone. Because students asking me, where are we using? Am I using a cell? Yes. Your mobile telephone or your handset is using a cell. That's a cell. Right? It has only two terminals, positive terminal and negative terminal. So what are you charging always is a cell. But what do you think after charging? Listen, stop writing. Have you ever used a phone which cannot which its battery cannot store charge for a long time? Have you ever used it? The answer is yes, right? What is happening? It means that if you charge, something is going on. There's a power loss within the battery itself, rather than the power consumption. Are we together? So that's the fact you have to know. So this theorem is used to maximize power. So today, when your parent will ask you, what did the Olenjolai teach you? And then tell them, he taught us about maximum power theorem that we are using to maximize power in our mobile phone. Right? In our laptop computers. Right? Because they have a battery and it's a cell. Wonderful. Okay. So, etc., you can mention some more examples. So, let us talk mathematically. So, mathematically, the maximum, say with me, maximum power theorem. The maximum power theorem, deduce the expression or deduce equation or deduce mathematical formula formula of resistance matching. And this is, we have a responsibility to show that internal resistance should be equal to the external resistance for the maximum power consumption. So I want to talk with you mathematically and deduce it. So the first is the derivation of the formula, of resistance matching. So the first state consider circuit below. So the circuit below. So this is switch K, and here we have load resistor R. So here we can place our voltmeter, which is direct current voltmeter or DC voltmeter, and measure potential difference there. And also you can place the voltmeter here to measure the electromotive force, if you do remember. No, the electromotive force across what? Resistance R. So this is ER. So if the switch is closed, this is say the second state. So from Ohm's law, we say that electromotive force is equal to current times external summations of external resistance and internal resistance. Then you do remember that we made I the subject and we had E over summations of external and internal resistance. So electric current is equal to electromotive force over external resistance plus internal resistance. This will be our first equation. Steady state, we call that, if you want to know the power consumed by resistance, listen, if you want to know the power consumed by the load, because that is our interest. What do you want? Stop rating my students. What are we doing or what are we learning? How we can maximize the power consumptions of the load, right? So our focus, we want to maximize the power consumed by the load, not by this one. Okay? So what will be the power consumed by the load? We call the formula of power consumption. Power consumption by the load. So the formula for the power consumption by the load is equal to, we can express in 3 forms if you do remember. It's electric current times potential difference across the resistor, or we can express as square of the voltage over resistance, or we can express as current square over R, that times R, right? So we are focusing, stop writing. We are focusing on power consumption by dotting by the load. This is an electric iron or your mobile phone or your television or your electrical appliance. Right? So this one will make equation 2. Then we go for the force state. The force state now, we say that substitute equation 2 into, no, substitute equation 1 into equation 2. So now, so what relationship? This is I, right? So replace I with E over R plus small r. So it means the power consumed by the resistor is equal to what? Electromotive force over external resistance plus internal resistance, and then squared times resistance. Are we together? So if we open the bracket, this is equal to what? Square of electromotive force times what? Load resistor, then of what? Summations of internal and external resistance squared. So, ladies and gentlemen, let us go into the fifth state. The fifth state, stop writing. Fifth state, we recall what we taught advanced secondary students in the one of the topic that called the differentiation, but also we taught in subsidiary subject that called basic applied mathematics to the students who are not studying advanced mathematics, the concept called the differentiation. So stop writing. So before I write the fifth state, let me write now the equation E square R, then R plus R squared. So this is equation 3. Stop writing. Local student, national, international students, stop writing at this state. Listen, I have a space there. So we go to the fifth state. The fifth state, we say that differentiate power with respect to load resistance. Differentiate power with respect to load resistance. Not electromotive force, not with respect to internal resistance. Right? So if that's the case, we say that in order to do that business, differentiate power with respect to by using what? By using a rule that we call the quotient or quotient. Is it like this? Quotient rule. Quotient. Quotient. My students are asleep. Is it like this? Quotient rule. So the quotient rule we taught you in basic applied mathematics and also in advanced mathematics that if, for example, we are differentiating dy, dx, let us recall from there, and then our function y, it is d dx of mean that divisions of the two functions, which is u and v. This is equal to what? So you say that you keep what? Keep u the subject first, and then keep v the subject. Keep v the subject and differentiate u with respect to x minus, we keep u the subject and differentiate v with respect to x, and then divided by v squared. We call this we taught you. If you have never been taught, then here's the good news. Don't worry again, we have a special playlist and we have a departments of basic applied mathematics. So this is the formula. So for that case, if that's the formula, everything is clear. So we can let, because you have this equation 3, we can let. So what should you do? So you say let U, this U, to be equal to numerator. Numerator we have square of electromotive force times resistance. Then we have to let what? Let V is equal to what? Denominator. Denominator is the resistance plus this one. That's why we say we need advanced or best or BAM. We need to apply advanced mathematics or different concepts of advanced mathematics or BAM in physics, in physics. And this is the one of the application, right? So now we want to find, according to the formula, we need du dx. Listen careful. Remember that. Remember that for our case. Then we have let x is equal to r. Right? Listen carefully. For that case, what are we looking for? We are differentiating power d dr of power, and this is equal to, if we differentiate power with respect to resistance, my students are copying, E squared times r over r plus r, then square. So we let x is equal to r. So if that's the case, we have u is equal to E squared r. To differentiate u with respect to r, this will give us what? This is similar if somebody asks you differentiating 5x. 5 stands for E squared. Students, I told you, stop writing low. 5 is equivalent to E squared. X is equivalent to R. So in BAM or in advanced mathematics, we told you that du dx, if you differentiate this one, differentiate 5x, will remain is constant 5. Similarly here, if we differentiate this one, E squared R, with respect to Sony is numbering. With respect to R. So we remain with what? So for this case, the answer is E squared. Right? So we found the U what? The R. So in order to avoid confusion, let me number this one as equation 4. Let me number this one equation 4. Okay, let me number this one as equation 4. And this one as equation 5. Okay? To avoid confusion. I'm not here to confuse you. I know now the PCB students, they have started to help the session. Yeah. Sabwaya one. Number PY. So that's how Swahili students used to say. Then we have V is equal to R plus this one, but what? Square. So writing. We need to differentiate V with respect to R because our X is R. Right? Differentiate this one. How do you differentiate this? We have to use a rule in mathematics called the chain rule. Now you see the beauty of basic applied mathematics. Why are we teaching you basic BAM? For this purpose. Then you say, oh, I will start BAM one day before exam. Okay. Keep with such mentality. So if you differentiate this one, 2 will come on this coefficient side. Then we have R, then plus this one. This is the simplest. Then here we have 2 minus 1. Then we multiply with derivative of inside of the expression we have inside the bracket. R it is constant. This is not a constant. It's just like somebody asked you to differentiate 5 plus x, for example. What will you get? If you differentiate 5 plus x, you get 1. Why? If you differentiate constant, you get 0. If you differentiate x, you get 1. Right? So if here we differentiate R, we get 1. If we differentiate the constant internal resistance, we get 0. Why? Because low resistance is variable. It's variable. Standard. So for that case, you say that dV dr, this is equal to what? 2 times what? external resistance plus internal resistance. 2 minus 1 is 1. 1 plus 0 is 1. So simply this is 2R plus R. So ladies and gentlemen, dV dr, this is equal to 2R plus R. This is second question 6. Tell your neighbor, physics is beautiful. Okay, so we have equation 4. Remember that this is equation 4. This is the equation 4. We have equation 5. We have equation 6. Then we go into the 6 steps of our derivation of resistance matching. So the 6th step, we say that we substitute equation 5 and equation 6 in equation 4. Okay? What are we looking for? We are looking derivative of power with respect to load resistance. What we have here, V. What is our V? Let V is equal to R plus R is equal to capital R plus small r square. So this is R plus R square. Then we need your du dx. But for our case, it will be dot du dr. Where's du dr? Du dr is equal to what? Du dr is equal to E square minus. Then we need U. What is U? U, it is E square R. It's E square R. Okay? E square R. Then we need dV dx. What is, but our expression is what? dV dr. Right? dV dr is equal to what? Is equal to 2R plus R. Then divided. We have what? V square. What is V? V let is equal to R plus 1. R, external resistance plus internal resistance is square. So we have R plus this one square and this one square. This is V and square. The next step is simplification. Okay. So the next step now is just a matter of simplification. So on left hand side we have what? D power dr is equal to. On this side we have what? E square R. If you didn't understand, watch this video several times until you understand every concept that I've been teaching you. R square. Then minus, we have minus here. Then we have 2 times this one, so 2 become a coefficient, E square. And then we have what? Resistance, open bracket resistance, external resistance plus what? Internal resistance. Then, in denominator, we have load resistance plus internal resistance square. Then we square, so it will be, because same base and exponent, it will be power 4. Okay? So if that's the case, we can see how we can simplify. The simplifications before we go into the graphical part, the PDR, this is equal to what? So R plus R is common. It's common. So in this part, we remain with E square R plus R. In this part, we remain with 2 E square times R. Then in the denominator, we have what? R plus R square, or 4. Then we simplify this with this. So you have derivative of power with respect to resistance. This is equal to what? Is equal to electromotive square plus this one minus 2 E square R over what? Over resistance plus R power what? Power 3. Okay, so ladies and gentlemen, let us continue with our interesting derivation of the formula for the resistance matching, or the condition for the maximum power consumed by the load. So the seventh step, so suppose that this is equation, so let us name this as equation 7. So this is equation 7 because the last equation is equation 6. So the seventh step, we say that consider the slope at maximum point of the graph of power consumed by the load against the load resistance. So let me sketch the graph and then I will show the maximum point. If you have any question, don't hesitate to ask in the comment section of this video. Okay, so this is the graph. Here it's the graph of power against the so power against the load resistance, which is R, and this is axis for power. So it's a graph, practically, according to physicists and electrical engineers, it's parabolic shape. So it's parabolic shape. So this is the maximum point. So this is the maximum point of this graph. So it's a maximum point, and at this maximum point we have the maximum power, and then this is the point that we'll see that at this point, maximum power, we derive the condition, but we say that suppose that this is point P. Okay, so point P. So here we have maximum power. So simply point P, it's what? It's load resistance at maximum power, comma, maximum power. So this is called the stationary point, which is the maximum point. That's what you call it in mathematics. So this is the graph that we have to consider. This makes figure 10.3. So it's titled as the graph of power against the load resistance. Power consumptions in the load resistor. So we go into the eighth state of this derivation. We say that at maximum point of figure 10.3, the slope of the curve at maximum point is 0. So let me just put this sentence in this way. So the slope of figure 10.3 at the maximum point, which is one of the stationary points, is 0. That to say that change in power with change in resistance is equal to 0, and this is at maximum point. That's according to the concepts of applications of differentiation in solving real-life problems. If you have any question, don't hesitate to ask in the comment section. So, from this fact now, that the gradient of this curve at point P, which is the P is respective to R, is equal to 0, this makes equation 8. We have equation 7 because of the space, so it's equation 7, and this is equation 8. So ladies and gentlemen, we go into the ninth. Let me take you into the ninth step, where that we call it equate equation 7 with equation 8. So equate equation 7 and equation 8. So to equate it, we have on left hand side we have 0 is equal to electromotive force square times load resistance plus internal resistance minus twice of electromotive force square times load resistance over what? Load resistance plus internal resistance power 3. So now, let us multiply by this to both sides. Let us multiply by this to both sides. So this one times 0, it is 0, is equal to what? Is equal to E square, resistance plus this, minus twice electromotive force square R. 0 times this is equal to 0, and then this one and this one will cancel. So from this fact now, we can bring this thing on the left hand side. So if you bring on this side, we have 0 plus 2 electromotive force square times resistance is equal to electromotive force square resistance plus this. So 0 plus 2 electromotive force square times R, this makes 2E square, resistance is equal to what? So if you open the bracket, is E square times resistance plus E square times internal resistance. So these are the like terms. So we can do subtraction minus E square R. This is E square internal resistance. So this makes electromotive force square times resistance, electromotive force square times internal resistance. So this one and this one cancel. Therefore, the expression for resistance matching, or the condition for the maximum power, the load resistance should be equal to what? Should be equal to external resistance. And that's what we call it in physics in resistance matching. Resistance matching. So let me do minor correction because of the time. So instead of calling resistance matching and potentiometer, let us call session 10 maximum power theorem. Maximum power theorem. Maximum power theorem of electric appliances. Maximum power theorem. Maximum power theorem, yes, maximum power theorem. And the resistance matching. So I will teach you about potentiometer in session 11. So it means that the condition for the maximum power consumptions at the load resistance is this, that the load resistance should be equal to the internal resistance. So that's why that we can say that for the maximum power consumption, for the maximum power consumption in the load resistor, the load resistor should be equal to internal resistance. Load resistance should be equal to internal resistance, like that. So it means that R should be equal to this. And this is what we call it in physics in resistance matching. So here we have a very interesting terminology which we call it resistance matching. Resistance matching. So you have a fundamental question. What is resistance matching? What is resistance matching? That's the question. So resistance matching is a process. Resistance matching in the process. Resistance matching in the process of matching the internal resistance of a cell with load resistance in order to maximize power. So remember to do that corrections of the name of the session is called the maximum power theorem and resistance matching. So resistance matching is the process of matching the internal resistance of the cell with load resistance in order to maximize the power consumption in the load resistance. So resistance matching is a process of matching the internal resistance of the cell with the load resistance in order to maximize the power consumptions in the load resistance. So resistance matching simply is the process of making internal resistance of the cell to be equal to the load resistance in order to maximize power. That is all about our maximum power theorem. So now let us go into problem solving. We had example 23. So this is example 24, and example 25 will be the homework. So you have to get prepared. Example 24. If you have any question, don't hesitate to ask in the comment section below. So example 24, it has two Roman A, an electric motor runs the scissors with electromotive force E and internal resistance R. Show that the power output of the source is maximum when current drawn by a motor is E over 2R. Then Roman B, for example 24, show that the power delivered by external resistance is given by the formula of power is equal to square of electromotive force times load resistor over the sum of load resistor and internal resistance squared. That the question we've been given, and we should solve it as well as we can in order to test our level of understanding on maximum theorem. The question is all about maximum theorem. An electric motor runs a DC source with electromotive force and internal resistance R. Show that the power output of the source is maximum when the current drawn by a motor is electromotive force over twice or 14 twice of external resistance. And then the second expressions, we have to show that the power consumptions, the power delivered by the external resistor, delivered by the external or delivered by external resistance is given by power by square of the electromotive force times load resistance over the summations of a square of the summations of load resistor and internal resistance. So solution. Solution. So an electric motor runs a DC source with electromotive force and internal resistance of that one. Show that the power output of the source is maximum when the current drawn by the motor is this. So solution. So we'll be following all the steps of derivation, but you can just summarize. The first stage, because it was a meter, because it was the first time, sketch the circuit. Sketch the circuit of electric motor. Sketch the circuit of electric motor. So here it's a circuit. So here we have electric motor. Present it by using the load resistor. And here we have switch K, so we have to close the switch. This is internal resistance, this is electromotive force, and this is load resistance. And if we close, this will be the total current flow. So this will be figure 10.4. DC motor electric circuit. So this is DC motor. So DC motor represented by using a resistor. Okay? So that's the first step. So second step, we say that from Ohm's law, we have an expression of electromotive force is equal to current plus times open bracket load resistance plus internal resistance. So from this we can make current the subject. We have this one, resistance plus R. So this makes our first equation. If you remember the concepts of resistance matching, then you can finish it. But it's better to show where we get that resistance matching. So we go into the third step. Third step, we say that power consumed by the load resistor, this is equal to square of direct current times load resistance. So this is equation 2. So the first, okay, so recall this. So the steady state. Recall the expression that we had. Recall the formula of power. So power is equal to square of the current times load resistance, and this makes equation 2. The first step, substitute equation 1 into equation 2. So maximum power is equal to electromotive force over load resistance plus internal resistance square times load resistance. So if you open bracket, this is square of electromotive force times load resistance, and here we have load resistance, then times square. Load resistance plus internal resistance is square. So that is the first step. So the fifth step, let us find out, let us differentiate power, find the derivative of power with respect to load resistance. So it means that we'll be differentiating power, which is equal to, if we differentiate square of electromotive force, this will be just a revision, a quick revision of the previous revision, like this. So to find the derivative of power with respect to resistance, we say that we use the quotient rule. We let this U and let this V. So the quotient rule state that we have, let's say, for example, we can say that this is V, the U, but we can go straight forward. Let us go straight forward. So V, this is V, so we write V here. Load resistance plus external resistance plus internal resistance square. Then we differentiate what? We differentiate U with respect to R. So if we differentiate U with respect to R, the derivative will be square of the electromotive force minus. Then we write what? U. U, it is what? E square R. Then we differentiate what? We differentiate the V with respect to R. So this one, if we differentiate, we get 2 first of all, then we get R plus R, then times what? If we differentiate the inner part, times 1. Then we have V squared. So our V squared is summations of resistor square times 2. We are starting power 2. So this is V squared. Remember that this is V. This is derivative of U. It means that this is denominator. This is derivative of numerator. This is numerator. This derivative of denominator. This is square of the denominator in this fraction. Because this is a fractional function. We use the rule, we call it quotient rule. So when we simplify carefully, we get the PDR is equal to what? Is equal to square of electromotive force, load resistance plus internal resistance square, minus what? We have 2, load resistance square, then times load resistance, then load resistance plus internal resistance, and then we have a denominator of summation of resistors power 4. So this will make equation 3. Okay, so suppose that this is equation 3 and this is equation 4. So the first step, we say that at maximum power, or at maximum point of the graph of power versus load resistance, the slope, the gradient. When you say gradient, it means delta power, change in power over change in resistance is equal to 0. So derivative of power with respect to resistance is equal to 0. This makes equation 5. Okay? So we are deducing the resistance matching. So the sixth step, we can take equation 4 and equate with equation 5. So the left-hand side of equation 5, the right-hand side of equation 5, which will become the left-hand side of equation 4, is equal to 0, E square times what? Times load resistance square, then minus what? Minus 2 E R plus R, then divided by R plus R power 4. We have two alternatives. We can simplify this term with this and this term, because R plus load resistance plus inter resistance is common. So we have 0 E square R plus this minus 2 ER. Then here we have what? We have load resistance plus this over 3. The next step, we multiply to both sides by denominator, then multiply the denominator to both sides, R plus this square. So on the left hand side we have 0 is equal to, so this one cancel this, 0 times this is 0, is equal to electromotive force square, then R plus R minus twice of electromotive square times R. So let us open the bracket. We have E square R, then we have E square internal resistance, then minus 2E square R. So bring it on this side, so 2E square R, this is equal to E square R plus E square R. Or even, there's no need just to do this one. So E square R minus 2 E square R, this will make 0 is equal to E square internal resistance minus E square external resistance. So bring this on this side. So we have E square external resistance is equal to E square internal resistance. So this one and this one is common. Then resistance, external load resistance should be equal to internal resistance. We didn't finish it. This is the answer or solution of example 24a. So this will make question what? This will make equation 6. So we have equation 6. So the seventh and last step to show what we've been asked in example 24a, we say that substitute equation 6 into equation 1. So you can check equation 1. Equation 1, we say that current is equal to electromotive force over summation of load and the load resistance and internal resistance. So you have to substitute it here. So external resistance is equal to R. So if you substitute, place, so here we have electromotive force, replace load resistance with internal resistance because they are equal at maximum power theorem, and this will make it electromotive force over twice of internal resistance. So you say that current is equal to electromotive force over twice of internal resistance, and this is, we conclude it, hence show. That is solution for example 24a. This is 24b. So, example 24b, the question asks you that show that the power delivered by external resistance is given by this. So we have to show the power delivered by external resistance is equal to E of what? Over summation of load resistor and the load resistor and internal resistance. That's what we have to show. So to show it, we say that this will be the 8th step, special formula B. We say that recall two equations. Recall equation 1 and possibly equation 2. So in equation 1, we say that I is equal to electromotive force over summation of load resistor and internal resistance. And then recall the general formula that power is equal to current times resistance. So this, we didn't number it, but now we can number it as equation 7. Equation 7. So we say that substitute equation 1 above. Remember that this was equation 1 into equation 7. So now the power delivered by load resistor is equal to electromotive force over summation of load resistor. Then we have to square it times load resistance. Then we conclude that hence show that the final solution. Then you are done. It could be a question of 5 marks. You have scored all the 5 marks that you have been rewarded. So, ladies and gentlemen, I believe that you have been learning this concept seriously. Right now, I would like to take you into the next important part. The next important part, which it's a time for the homework. So this will be homework 10, and it's example 25. So it's additional question to what that we have taught you before. And it's not a difficult question, actually. I took this question from reference book, refer A-level physics books by Roger Mancaster. Roger Mancaster, page 553. Here is the question. A battery of EMF 60 volt, EMF 60 volt, and internal resistance of 2 ohm is connected across a torch bulb with a resistance of 10 ohm. Calculate Roman 1 current, Roman 2 power consumed by in internal resistance This is Roman 3. This is Roman 2. Power consumed by the bulb and then Roman 4 ask you to verify that total power supplied by a battery is equal to product of electromotive force and the current it supplies. So, ladies and gentlemen, that is the second question of the homework. Let me read it. A battery of electromotive force 6 volt and internal resistance of 2 ohm is connected across a torch bulb with a resistance of 10 ohm. Calculate current, Roman 2, power consumed by the bulb, Roman 3, power consumed in internal resistance, and Roman 4, verify that total power supplied by the battery is equal to the products of electromotive force and current it supplies. Make sure that you do that question and you give us feedback in the commenting section of this video. So, ladies and gentlemen, this is the end of session 10, which I have done the correction entitled as maximum power theorem and resistance matching. Thank you very much for joining me. I would like to invite you in session 12, in session 11, where I will teach about potential divider. You have to stay tuned. And the next topic will be finishing, means that we are about to finish in session means chapter 1. We may go into chapter 2, which is complex circuits or Kirchhoff's law. And then this is all about session 10, about maximum power theorem, but you are allowed to go in depth by using different reference books. I have just a couple of announcements before I end this session. The first two announcement, part A, is make sure that you use the comment section to give me the feedback and to ask you questions as well as you can. The second announcement, means the first announcement, part B, we have also established the Tanzania Online Advanced Library, where we use to equip our students with some relevant materials such as textbook, syllabus books. Okay, syllabus books. This is physics syllabus for advanced secondary education from 5 to Form 16, prepared by Tanzania Institute of Education. This is Principles of Physics. It's a book used by advanced secondary students worldwide. It has been written by PhD physicists in India. And then this is the original scientific calculator that's called Casio Function 991 MS. So you can order all of these contents or some contents, some of these books. We have notes, you can order notes, you can order textbook, you can order questions and solutions book, you can order syllabus book, you can order scientific calculator. The only thing that you have to do, send to us an SMS through this number, 0759745331. The last announcement before we recall the day is if you feel from your heart you want to offer our living God your feeling thanksgiving of any amount through this program, you are warmly welcome, and the doors are open, and this is the word of faith from the Holy Bible. Read that scripture and offer it by faith. You may offer feeling thanksgiving of any amount. 50 Tanzania shillings, 1,000. You can offer feeling thanksgiving of 10,000, 1 million, 100,000, 100 US dollar of any amount. And your feeling thanksgiving will be used to pay for the running cost so that more videos of advanced physics, advanced chemistry, advanced mathematics, basic mathematics will be recorded and published into the present and future generation. So just send your feeling thanksgiving through the telephone number 0759745331. And this is the end of these sessions. Let us give God thanks, because we began with God and we end this session with power of God. Our Almighty God, we come before your presence as your children. We say thank you. I thank you myself as a teacher. Thank you for the fresh anointing that you have given me during the preparations and even at the time of teaching, that I taught your students in extraordinary level compared to how I used to teach these concepts to the previous students. Father, I thank you and I give you all the glory and praise. And even the students who have been watching me, I don't deserve any praise or glory, but I have to give you all the praise and glory because you are the living God. Thank you for this opportunity. Thank you for the understanding. Thank you for the comprehensions. Thank you because you have become a transmitter, medium, and receiver. And thank you because you are going to market, you are going to distribute these contents to millions of Form 6 advanced secondary students in the entire country of Tanzania and worldwide. We give you all the praise and honor. Amen. So, join me in the next session. That will be session 11. And this is Olenjolai from Tanzania. Keep enjoying the beauty of physics. See you in session 11.